So today we're going to have a look at Newton's 3 laws of motion. We're going to talk about what those laws are. We're going to see if we can get to grips with them, actually understand them, and see if we can apply them to a situation. Newton, whose laws of motion they are, was probably one of the most famous scientists there ever has been. Born in 1643, died in 1727, survived the Great Fire of London, survived the plague the year before that. Probably most famous for his work in forces, motion and gravity, but forces and motion, the branch of science known as mechanics, how things move, how forces affect things that move. Units of force are named after him. So what his laws tell us is how, when you apply a force or you don't apply a force to an object, what happens to its motion. If we apply a force, how will its motion change? If no force is applied, what will happen to the way that it moves? So here's a bit of an animation. I've got a guy holding a ball, and he throws the ball in one direction, and he's stood on a skateboard, and so he moves off in the other direction. Newton's laws will help us to answer these questions. I'm not going to answer them right away. We're going to have a look at what we got here, and then we're going to see if we can answer them by the end of this video. Why does the person stay still at the start? That's question number 1. Why does he start to move when he throws the ball? Why does he move slowly when the ball is moving quickly? And why does he go left when the ball goes right? So those are the things we're going to be looking at and hopefully getting to grips with over the course of this video. So the 3 laws, let's look at what the 3 laws are. Newton's first law is an object will remain at rest or continue with a constant velocity unless acted on by a force. And here's a pretty good example of this. Here's a kid going along at a constant velocity until, bang, he gets acted on by a force, and that changes his velocity, changes his motion, changes the way that he moves. So an object will remain at rest, or in this case, continue with a constant velocity unless acted on by a force, and bang into the tree provides the force there. His second law, the force on an object is equal to the mass of the object multiplied by its acceleration. This is exemplified by one of the most well-known equations in science, F equals ma, force equals mass times acceleration. His third law is every action has an equal and opposite reaction. This guy here firing a rifle, smacked in the face because the bullet goes in one direction with a certain amount of force, and that forces the rifle in the opposite direction, smacking him in the mouth. So let's look at the first law first of all. So that first law, just to remind you up there at the top right, an object will remain at rest or continue with a constant velocity unless acted on by a force. Let's look at this particular bit. An object will remain at rest unless acted on by a force. Let's just look at that little chunk of it first of all. So we imagine a ball sat on a table. We're not going to touch the ball, so by not touching it, we're not going to be applying any kind of force to it. What do you think is going to happen? Now, this is a point where you could pause the video, have a bit of a think about it, see if you can answer it, and then I'll reveal the answer. So nothing will happen. Nothing's going to happen because Newton's first law tells us that the ball will remain stationary, so at rest, not moving, unless it's acted on by a force. And because we're not applying any kind of force to it, that means it's going to stay put, it's going to stay where it is. Okay, so we're going to change the scenario ever so slightly. We're going to now apply a force of 10 newtons to the ball. What do you think will happen now? And again, a good time to pause, have a bit of a think, and then you can come back for my answer in just a sec. The ball will move in the direction of the force. So the force was in the direction to the right, so the ball will move in that same direction. Force is a vector, and force will cause an object to have a velocity by accelerating. Both velocity and acceleration are vector as well, and they get the same direction as that force that was applied to it. And again, we know this because Newton's first law tells us that it's going to remain at rest unless acted on by a force, and it's that last bit there, unless acted on by a force, that tells us that in this case, the ball is going to move because there is a force acting on it. Let's look at the sort of second half of this bit here. So an object will continue with a constant velocity unless acted on by a force. We now have a ball and it's moving through the depths of space, just flying through the depths of space there. It's moving, but there are no external forces acting on it. What's going to happen to the ball? If it's flying through the depths of space, there's no atmosphere, no drag, no air resistance, nothing like that. What's going to happen to it? The ball should keep moving in the same direction with the same velocity. Newton's first law again tells us that it will continue with a constant velocity unless acted on by a force. So that's what it's going to do. It's just going to continue going. It's not going to get any faster. It's not going to get any slower. It's not going to go left, right, up, or down. It's just going to go in the same direction with that same velocity. Remember, velocity is like the vector version of speed. It's speed, but in a given direction. In this particular case, it was down to the bottom right. Okay, another scenario for you. Our ball is still flying through the depths of space. There it is, but you may have noticed I'm now inside this planet here. We're going to call this planet the planet Floob. What's going to happen is this ball's going to smack into the planet Floob. What's going to happen to the ball? It's going to stop moving, of course. Its velocity is going to change. It's going to smack into the planet, and its velocity will change. Newton's first law is the thing that tells us this is going to happen, because it's going to continue with a constant velocity unless acted on by a force. And this planet, which I call Floob, provides a force that will change its velocity. So the force is in the opposite direction to the ball's motion, and so the ball comes to a stop. So we sometimes call Newton's first law the law of inertia. So what is inertia? It may not be a word that you've heard before. What is inertia? Well, the technical definition is the tendency of an object to stay at rest or continue in uniform motion, which is pretty incomprehensible. So let's see if we can work out what that sentence itself actually means. Well, the more mass that something has, the more inertia it has. So things that have more mass, bigger things, have higher amounts of inertia. So we could say that higher mass equals higher inertia. I've got two people here. I've got a sort of reddy-orange person and a sort of greeny-yellow person. The reddy-orange person is bigger. They have more mass, so they have more inertia. The little yellowy-green person has a lower mass and so has a lower inertia. Now, the more mass that an object has, the harder it is to change its motion. And you can think about this maybe if you were to think about kicking a balloon. If you kick a balloon, you put in a certain amount of force and the balloon moves very quickly away from your foot. You put in a certain amount of force and it accelerates very fast away from your foot. If you were to do the same thing to a bowling ball, if you were to kick a bowling ball as hard as you kicked the balloon, you'd probably end up with quite a sore foot for a start. But the bowling ball certainly wouldn't move away from your foot nearly as fast as the balloon did. And that's because the bowling ball has a higher mass and so has more inertia. It's harder to move it. It's harder to get it to change its motion than it is something that has less mass, because the bowling ball has more inertia. So higher mass means harder to move. We've already said, though, that if something has a high mass, it has a high inertia. So if something has more inertia, that must mean that it's harder to move. Higher inertia means that it's harder to move. We know that because we know that higher mass is the same as higher inertia. We know that higher mass is the same as harder to move, so therefore higher inertia must also mean harder to move. Let's have a look at our definition. Our definition is the tendency of an object to stay at rest or continue in uniform motion. Let's make that a bit easier to understand. Let's go with how much an object resists motion due to a force. So if we apply a force to an object, how much does it resist being moved? If it has a lot of inertia, it will resist a lot. If it has a low amount of inertia, it won't resist very much. It'll be moved a lot more. So let's test this out. We've got this person here. The person on the left has a high mass, so therefore they have a high inertia. This should mean that they're quite hard to move when we chuck at a ball at their head with a certain amount of force. And shock horror, they've been moved only a little bit. They're harder to move because they have a higher inertia. Now this smaller person has a lower mass, and so therefore a lower inertia. So when I chuck that same ball with the same force, along comes the ball and, oh my gosh, they've been moved an awful lot. Because they have a low inertia, they are easier to move. So inertia, how much an object resists motion due to a force. Have a look at the second law then. So Newton's second law is the force on an object is equal to the mass of the object multiplied by its acceleration. And this is exemplified by the equation F equals ma. Force equals mass times acceleration. Three things that I want to look at with Newton's second law. The three main things that I think Newton's second law really tells us are that when you apply a force to an object, it's going to accelerate. If you apply a force to something, it's going to move in a particular direction with a particular velocity. And if you continue applying that force, its velocity is going to increase. So it's going to accelerate. If you apply a big force, you're going to get a big acceleration. The converse is also true. If you apply a small force, you're going to get a small acceleration. And the last thing is this: the bigger the mass of the object, the less it will accelerate when the same force is applied. So let's have a look at these three things and see if we can make sense of them. So the first of these rules was, when you apply a force to an object, it will accelerate. Or at least it will whilst the force is being applied. So if the force is still being applied, the thing should get faster and faster. When the force stops being applied, though, it should just continue with a constant velocity. Remember, if there's no force being applied, Newton's first law tells us that something will just continue with a constant velocity or remain at rest. If it already has a velocity and there's no other forces, no drag, no air resistance, nothing like that, it should just continue with a constant velocity. So I'm going to apply a force of 10 newtons to the right, and we'll see what happens. It should start off slowly, and its speed should increase. It got faster, it accelerated as it went through, and that's because a force was being applied. When you apply a force, it causes an object to accelerate, and that's one of the first things we need to understand with Newton's second law. The second thing was this: the bigger the force, the bigger the acceleration. So if we apply more force, we should get a larger change in velocity. Remember that when something changes velocity, that means that it's accelerating. The bigger the change in velocity, the bigger the acceleration. So let's apply a force of 10 newtons to that top ball and a force of 5 newtons to the bottom ball. Remember, these balls here, they're the same size, so we're going to assume that they're the same mass as well. So big force to the top one, small force to the bottom one. They should both accelerate, but with different accelerations. And there we go. So the 10 Newton ball gets accelerated faster. Its velocity increases at a faster rate than that 5 Newton ball. Let's look at it one more time. 10 Newton ball, its velocity is increasing, but it's increasing faster than the 5 Newton ball is increasing. So the bigger the force, the bigger the acceleration. The last thing is this: the bigger the mass of the object, the less it will accelerate when the same force is applied. This also comes down to inertia. Remember, inertia is how much an object resists motion when a force is applied. If something has a high inertia, that means it has a high mass. This bottom ball has an inertia or a mass of 20 kilograms. The top one only 5 kilograms. So we should expect that bottom ball to accelerate less. It has a higher inertia, so it's going to accelerate less when the same force is applied. So I'm going to apply 10 newtons to both balls, and we'll see what happens. Shock horror. The ball with the smaller mass accelerates faster than the ball with the larger mass. So this is because, again, Newton's second law tells us the bigger the mass of the object, the less it will accelerate when the same force is applied. And again, as I said, it comes down to inertia as well. Higher inertia, harder to move. So this GIF here shows us quite nicely Newton's second law, but I think it shows us two things quite nicely that we've just discussed about Newton's second law. It doesn't really show us one of the things that we've discussed. So what are the two things that it does show us? What's the one thing that it doesn't show us? Pause the video, have a bit of a think, and then come back for the answers. The first thing that I think this GIF does demonstrate quite nicely is that if you apply a force to an object, it's going to accelerate. When the leg comes down and kicks the bowling ball, it moves, it accelerates, it starts to move because a force is being applied. And the balloon as well, when a force is applied, will also accelerate. It also shows us quite nicely that the bigger the mass of the object, the less it will accelerate when the same force is applied. So the bowling ball doesn't accelerate very much. The balloon accelerates quite a lot. So those two things are shown quite neatly. What it doesn't demonstrate, though, is that the bigger the force, the bigger the acceleration. By having this prosthetic leg set up thingamajiggy where it swings down, we're essentially meaning that the force is going to be the same each time. It's a nice way to make sure the force is the same each time. So we're not increasing the force. So the thing we're not able to see is that the bigger the force, the bigger the acceleration will be. The third law. Let's look at the third law. I like to think that it's a bit like karma, Newton's third law. Whatever you put out into the world, karma says, is what you'll get back. So if you're nice to someone, the idea is that you will have nice things happen back to you. If you're mean to someone, you should expect that mean things will happen to you as well. Newton's third law says that every action has an equal and opposite reaction. So if you do something, if you apply a force in one direction, you should see that same force coming back to you but in the opposite direction. So let's think about this. Here I am leaning up against a wall. I'm applying a force against this wall. This wall is nice and sturdy. 10 newtons I'm applying on the wall. Now the wall is going to apply a force of 10 newtons back as well. This gives us a resultant force of 0 newtons, meaning that there's no acceleration happening. Nothing should be moving. The wall should stay put. And this is what we tend to see in everyday life, and you've probably done it before. I would bet you any money that you've probably leant against a wall before. And when you leant against that wall, the wall stayed put. And that's because you were applying a force to the wall, and the wall was applying the same force but in the opposite direction back at you. The resultant force was 0, and the wall didn't move. Let's look at what would happen in some kind of weird alternative universe where this was not the case. Let's say that every time you pressed against a wall, the wall pushed back, but with only half the force that you applied to the wall. In that particular universe, what would happen is you would both fall over, you would both move to the right. The resultant force would be 5 newtons to the right, and so you would fall down. Not good. Now, let's say that when you apply a force to the wall presses back, but it presses back with a bigger force in this strange alternate universe. What would happen then is we'd have a resultant force of 5 newtons to the left, and the wall would fall on top of you. Everyone would be incredibly scared of touching walls because the wall would always push back with a greater force than was applied to it. Walls would be falling and crushing people all the time. And that definitely can't be right. So Newton's third law tells us that for every force in one direction, there'll be a matching force in the opposite direction. For every action, there's an equal and opposite reaction. So we can be sure that when we press up against a nice sturdy wall with a force of 10 newtons, that we're going to get a force of 10 newtons pressing back, meaning that the resultant is 0, and we're not going to have anybody being crushed, which is good. So if you fire a gun, the bullet is forced in one direction. In this particular example here, he's firing a gun. The bullet's going to the right, but you should notice that the gun is also going back to the left. Now, the reason is because of Newton's third law. If there is a force in one direction, there must also be a force in the opposite direction. The bullet's going in one direction, it's being forced in one direction. So the rifle, the gun, has to be forced in the other direction. Now, the rifle's mass is going to be much, much bigger than the mass of the bullet. The bullet might have a mass of 5 grams. The rifle might have a mass of 5 kilograms. So it might be a whole sort of 1,000 times bigger than the bullet. This means that you get less recoil, you get less acceleration of the rifle backwards compared to the bullet. The equation which sums up Newton's second law quite nicely is F equals ma. If we rearrange that, you can see that A equals F over m. Now, Newton's third law tells us that every action has an equal and opposite reaction. So if there's a force in one direction, there must be an opposite force of the same magnitude in the other direction. So the force number will be the same. The only thing that changes is the mass. If the rifle has a higher mass than the bullet, then it's going to have a lower acceleration. Which is why you can fire a rifle without ripping your shoulder off. So just to quickly recap the 3 laws, we've got Newton's first law, which tells us that an object will remain at rest or continue with a constant velocity unless acted on by a force. And this GIF shows us something with a constant velocity that then gets acted on by a force, that force being the tree, and then he remains at rest quite nicely. Newton's second law says that the force on an object is equal to the mass of the object multiplied by its acceleration. That's F equals ma. And the last one, Newton's third law, is that every action has an equal and opposite reaction. If you apply a force in one direction, you're going to get the same force, but in the opposite direction. Fire the gun, bullet goes one way, gun goes the other. Wonderful. So we're going to use Newton's laws of motion to answer these questions. And when you do answer these questions, you should pause and have a bit of a go at answering these. When you do answer them, you should try to use Newton's laws to do that. First question, why does he stay still at the start? So before he throws the ball, why does he not move at all? Second question, why does he start to move when he throws the ball? Third question, why does he move slowly when the ball is moving fast? And the fourth question, why does he go left when the ball goes right? So pause the video, have a go at answering the questions, and then when you think you've had a bit of a crack at it, unpause and we'll see what we've got. First question, why does he stay still at the start? Well, Newton's first law tells us that an object will remain at rest unless acted on by a force. And because there is no force acting on him, the person is going to stay still. He's going to remain at rest, he's going to remain stationary. He is not having a force acting on him. Newton's first law tells us he's just going to stay still. So the second question, why does he start to move when he throws the ball? Well, first of all, let's look at Newton's first law again, which tells us that an object will remain at rest unless acted on by a force. When he throws the ball is acted on by a force, so the ball starts to move. Why does he start to move as well? Well, in order to explain why he also starts to move, we need to bring in Newton's third law, which tells us that every action has an equal and opposite reaction. So if he exerts a force on the ball will also exert a force on him. If he has a force being exerted on him, he's going to start to move. You apply a force to something, the idea is that it will then start to have motion, it'll start to move. Third question, why does he move slowly when the ball moves fast? So he throws the ball, ball moves away quite quickly, he moves away quite slowly. Well, let's start with Newton's third law. Every action has an equal and opposite reaction. So the ball exerts an equal force on him, just in the opposite direction. He's applying a force to the ball exerts the same force on him, just in the other way round. Let's now bring in Newton's second law, which is about how the force on an object is equal to the mass of the object multiplied by its acceleration. The force on him and the force on the ball are the same, they're just opposite, so one's positive, one's negative. But he will have a much lower acceleration because he has a much higher mass. So we've got that F equals ma. You can rearrange it to A equals F over m. The force is the same, that F is the same, but his mass, the m, is much, much bigger. So he's going to end up with a much lower acceleration than the ball does. Why does he go left when the ball goes right? Well, we need to bring in Newton's third law for this one. The ball will exert an equal force on him, just in the opposite direction. As the ball is pushing to the right, he will experience the ball pushing him to the left. That's that. So Newton's three laws of motion. An object will remain at rest or continue with constant velocity unless acted on by a force. That's the first law. The second law is the force on an object is equal to the mass of the object multiplied by its acceleration, F equals ma, that classic mechanics equation. And the third law, every action has an equal and opposite reaction. If you apply a force in one direction, expect to get the same force back in the opposite direction. Bullet goes one way, rifle goes the other.